Okay, welcome to lesson number 2. This is our first organic family called Haloalkanes. Just a quick review, remembering that an alkane is a long carbon chain that contains only single bonds. So this part is going to be much easier than we had for the last few weeks, naming all those branched chain alkenes and alkynes. We're going straight back to the alkanes. So short straight chains, and we're just going to add the functional groups to it. So in the haloalkane family, the functional group that it contains is the halogen. So adding either fluorine, chlorine, bromine, or iodine to that main chain creates us a haloalkane. The general form, and for all of these chemical families, R denotes the chain. So that is the carbon chain. And then X, in this case, is the halogen. So anytime you see an X, that is referring to the halogen that we've put in there. So that's the general form, and the definition would be an alkane that contains a halogen. So when we're coming to name these compounds, they are going to be very, very similar to the names of alkanes. So those roots we learned, like methyl, ethyl, propyl, we are still using those roots to the name, and we're still ending the name in A-N-E. The only difference is now we're putting a numbered prefix and whatever the halogen is into the name. So the root of the name, just like it says in blue here, is the longest straight chain. I promise I will not give you branch chains to add that on top of it. So we'll just be naming straight chain ones. The root to the alkane is where we get that root, so count the number of carbons. That's how we get that root number. The type of halogen determines the halo prefix, so chloro, bromo, fluoro, iodo. And the chain is numbered so that the lowest number is the halogen. That's pretty much exactly like we were doing for double and triple bonds, only now we're going to make the lowest number the halogen side of the chain. Okay, so I've got two examples here for you. In the first one in purple there, if I wanted to figure out the name, I know it's written there for you, but if we're going over how to figure out the name, I'm going to go through and find my main chain, just like we used to do. So there's our main chain, and our main chain has 5. So I need to start numbering my chain closest to the halogen. So that means I'm starting to number my chain at this side. So that would be carbon number 1, 2, 3, 4, 5. So 5 is pent. It's all single bonds, so it's ane. And the halogen is at carbon number 1, and it's a chlorine, so it's chloropentane. Notice there's no space between the chloro and the pentane. No hyphen, no space, no comma. Looking at the next one, again, going through this sort of same process. How many carbons? 1, 2, 3, 4, 5. So again, I'm looking at pentane. My chlorine's closest to the left-hand side. So now I have to start numbering 1, 2, 3, 4, 5. So it's 2 chloropentane. Try these next two examples here for yourself to see if you can understand how to name the chain. Okay, hopefully you did the same as me. You highlight your main chain there, and we know that that main chain is 4 long. So the root of the name is going to be bute, and again, it's all single bonds. It's important to note that it could be double or triple bonds, but we won't be doing that. We're just going to stick with alkanes. So 4 carbons is bute, so it's butane. And now I have to figure out what the number of the carbon is. And so I go closest to the halogen. So it's going to be at carbon number 1. So it's going to be a 1-chlorobutane. Okay, over on the second example there, my carbon chain is 3 long. And I know that 3 is prop, so it's propane. Now, we know in the double bond and triple bonds, we didn't ever have to have a number with propane, but here we do, because it could be on carbon number 1 or carbon number 2. So in this instance. Doesn't matter what end I number it from, it's going to be carbon number 2. So that's 2-chloropropane. Okay? So that's sort of how you name them. Their structures are very similar to hydrocarbons. And again, like I mentioned, it can be alkanes, alkenes, or alkynes, but we're going to stick with alkanes. One hydrogen has been replaced with, so it's hydrogen that's been replaced with the halogen for the structure. Now, is it possible to have more than one? Yes. We are not going to get any complicated examples like that, but just know that, yes, it is possible to have more than one on one molecule. Okay, so now when we start talking about properties, we're going back to what we talked about in functional groups, that as soon as I introduce that electronegative atom, I have increased the intermolecular forces of that compound. So when I increase the intermolecular forces and I make it a polar compound, I've increased the boiling points and melting points. So if we're comparing them to alkanes, alkenes, and alkynes, because this is our first new organic family, they are higher boiling points than those hydrocarbons. So the polarity is going to depend on the type of halogen. So something with a fluorine attached to it is going to be more polar than something with a chlorine attached to it. Okay, so it works sort of the same way that they're written in the periodic table. Fluorine is more reactive, so more electronegative. So if it has a fluorine versus a chlorine, it would have a higher boiling point with the fluorine than it does with the chlorine, and bromine and iodine and so on. Important to note that there is no hydrogen bonding. I do not have that OH or the NH group, so it does not have hydrogen bonding. It is insoluble in water, because it doesn't have that hydrogen bonding, right? Although it makes it a little bit polar, they are not polar enough to be soluble in water. And again, just like all of our alkanes and alkenes and alkynes, they will take part in combustion reactions. So that's sort of a summary of the properties of haloalkanes. Now, more important than the properties, we want to focus in this unit or this chapter on the applications to real life. So the interesting facts we're going to present about each family are going to give us the ideas of the applications. So the most important application of haloalkanes is our CFCs, or in other words, chlorofluorocarbons. So this is kind of a hot topic in terms of the chemistry and the environment. So these are molecules that are often used as refrigerants and propellants in aerosol cans. They're used to generate plastics and solvents for dry cleaning. They are non-flammable and they're not very toxic, but they are not good for the environment. These are those compounds that are responsible for the destruction of our ozone layer. So in many countries, they've actually been banned. And here in Canada, they are no longer used as propellants for aerosols. And we've come up with much more environmentally friendly refrigerants. So these compounds are no longer found there. But interestingly enough, they were. They are also used in pesticides. So they're not very toxic to us, but they do have effects on other pests. Okay, so just some applications of haloalkanes. So you will have some practice naming some haloalkanes. So here are 4 molecules for you to try naming. Again, please comment or send me a message if you are struggling and not sure how to name or describe haloalkanes.